Hello, today we're gonna talk about my CS50 end project. So I'm gonna present it here. Let's see if everything is recording. Yeah. So this is my CS50 end project. It's a quantum computing inspired with users input. So users can input using the Circ Google Quantum Computing Library in Python. Well, my name is Alexander van Zoelen. My GitHub name is Snorfetched. This is my EDX name, Christian Huygens. I come from Den Haag or The Hague in the Netherlands, and the day of recording is 19 April of 2025. 19th of April. So, why did I choose it? Well, I study physics. I'm a physics student, and I really enjoy quantum mechanics. So that's why. And I was really inspired by quantum computing, which is basically, I'm gonna explain it a little bit really quickly because we only have 3 minutes. But you know your normal computer, well, this is a quantum computer which uses the laws of quantum mechanics. A normal computer has a 0 or 1 bit, but and you can switch either to 0 or to 1, but a quantum computing system, a qubit, a quantum bit, can be in 1 as well as at the same time in 0, so in 2 states at once, which is called superposition. A qubit can be in a superposition of 1 and 0 at the same time. That's a quantum mechanic principle. Not only that, but a qubit can also have another quantum mechanic principle called entanglement, where a qubit is dependent on another qubit. Basically, if one qubit changes its state, the other qubit changes its state as well. It's entangled with each other. And a quantum computing system applies gates to the individual qubits to form operations just like a normal computer. So that's a bit of a short summary of quantum computing. Well, I use Circ, which is a Google Quantum Library made by Google. I used to do Qiskit first, but I tried that, but it didn't work. So now and Circ works, so we're gonna use the Google Quantum Library. And to showcase my code, we're gonna see 2 operations in action. One where 2 qubits and the X gate is applied to the 0 qubit, and the CZ on the 0 and 1, and the 3 qubit operation where we're gonna have 3 qubits with a Hadamard gate, a very important gate in quantum computing, as well as the CX01 gate and the CX12 gate on them, which we're gonna see is a maximally entangled 3 qubit state. And the CZ and the CX and the CX are just variants, are just specific gate operations used in quantum computing. So that was a little presentation. Now we're going to really dive in deep into the code. So this is the code, and I used a bunch of metacode, like you can see, to explain it, which is also going to be in a README file. This is the little test project to see if everything works in our requirements. We use the Circ library, the matplotlib, to showcase our histogram where we can see the quantum state and how many times that has been in the quantum state, and a PyTest. Because in quantum mechanics, when measurement is being done, the state collapses into one state. So the superposition collapses into one state, which then we measure. So, and because it's probabilistic, it's quantum mechanical probability, it collapses to one state, and then we can measure. And if we, for example, do 1,000 times, 1,000 shots, it's what's called in quantum computing. If it's 50-50, 500 shots should be in the first state and 500 in the 0 state, because it's the 50-50 probability. And this probability distribution, it depends on our quantum circuit, of course. So, this is the whole premise of the code. The user implements a number of qubits and gates on the gates that are applied to the qubits, and then this is according to our get gate input. And then on a build circuit, we build our circuit using official Qiskit documentation, like you can see here. And for every gate, we applied it to the relevant qubit. You can see to my code, but we need to speed up because we only have 3 minutes. So this is just for binary output, because circ outputs it into an integer, but we want to have it into binary, which is way more common in quantum computing. And this is where our histogram is going to be printed out. So we want a Python project. We want to implement our two operations today for you so you can see. First, we have 2 qubits. We're going to use 2 qubits, and what's our gate sequence? It's x0 and cz01. So this is our result. This is our quantum circuit printed out. The x is being applied to the 0, and then our cz gate, and this is our measurement, the m. Now the bar chart is in the histogram file, which we're going to open now. And what this does, we're going to see is here, yeah. So what this operation specifically does, both qubits start in the 0 state. We use the x gate to move the 0th qubit to the first to the state number 1, and then the cz gate applied, which makes a phase change. But the phase change isn't relevant when there's no superposition, because there's no superposition because the qubit only started in the 0th, and now it's to the 1st state. So this is our result of the quantum circuit. 1,000 shots, I think it's mentioned here in the 1,000 repetitions in our code, and all the shots have been measured in the 1-0, which in quantum computing means the first state, which makes sense, like I just explained. Now we're going to do the three qubits, and the first one is to implement the Hadamard gate, the H gate, on the 0th qubit, and this creates a superposition on the 0th qubit. So we're going to do Python project .py again. We're going to have 3 qubits this time, and we're going to Hadamard gate on the on the 0th qubit, the CX gate on the 0th and 1 qubit, and another CX gate on the 1 and 2 second qubit. And now this creates a maximally entangled state. So we're going to have a look. We're going to close this histogram again. We're going to have a look at the results. So this is our result. The Hadamard is implemented on the 0 qubit. Now we have the X gate on the 0 and the 1st, and now another X gate on the 1st and the 2nd, which is now measured all 3 times. And we're gonna see that all 3 states. You're gonna see it on the histogram file. That this makes sense. So this is maximally entangled. It's a 50-50. A kind of Bell state for 3 qubits. The first one is a 0-0-0 state, where all 3 qubits are in the 0 state, and the second is a 1-1-1, where all the 3 qubits are in the first state. So yeah, that is our little demonstration. All the specific details of the code I wrote in the metacode and in the README file, of course. So I want to thank you. I hope this is under 3 minutes. Well, this is the video. Okay, bye.